2146. One might begin by considering a simple fact, a fact so strange that even now, after all these years, I find it arrests the mind in a way that few things in physics do. The element that destroyed Nagasaki, the element that lay at the heart of the Trinity device, the element that became the foundation of nearly every nuclear weapon in the arsenals that followed, does not exist in nature. Not in any meaningful sense. Not in the rocks, not in the sea, not in the stars we can observe, not in the Earth's crust, where the other 91 naturally occurring elements reside in their various abundances and combinations. Plutonium, element 94, atomic mass 244, is, for all practical purposes, a human creation. We made it. We made it in a laboratory, in a cyclotron, in a reactor, atom by atom at first, and then by the kilogram. And we made it for one purpose, and one purpose only, though we dressed that purpose in the language of science and discovery and national defense. We made it to build a bomb. I should like to think a little about what that means. What it means to create an element. What it means that nature did not provide this particular substance, and we provided it ourselves. And what it means that the thing we provided has shaped the political and moral landscape of the world more profoundly than perhaps any other single material in human history. Because there is something in this story that goes beyond physics, beyond chemistry, beyond the technical narrative of how element 94 was first synthesized and then produced on an industrial scale. There is something in it that touches on the oldest questions we know, questions about the relationship between the creator and the created, about the boundary between the natural and the artificial, about what happens when human beings acquire a power that was not in any obvious sense intended for them. The Greeks told the story of Prometheus. The book of Genesis tells the story of the tree of knowledge. The Bhagavad Gita, which I read many times in Sanskrit with Arthur Ryder at Berkeley, in those years before the war when physics still seemed to me a thing of pure and uncomplicated beauty. The Gita tells of Arjuna's terror when he sees the true form of the divine, a form that contains all creation and all destruction in a single vision. These stories are not the same, but they rhyme, and the story of plutonium rhymes with all of them. Let me be precise about the physics, because the physics is where the moral weight originates, whether we wish it to or not. Uranium, as it exists in nature, consists overwhelmingly of two isotopes, uranium-238, which makes up 99.27% of natural uranium, and uranium-235, which makes up a mere 0.72%. It was uranium-235 that was fissile, that could sustain a chain reaction, and the immense difficulty of separating it from uranium-238, atom by atom, in sufficient quantities to build a weapon, was one of the great technical challenges of the Manhattan Project. The gaseous diffusion plant at Oak Ridge, Tennessee, consumed more electricity than the city of New York. The electromagnetic separation process, the calutrons, required magnets so enormous that we borrowed 14,000 tons of silver from the United States Treasury to wind their coils, because there was not enough copper available in wartime. All of this to extract, with painful slowness, a few tens of kilograms of uranium-235 from the vastly more abundant 238. But uranium-238, the supposedly useless isotope, the dross, the residue, the 99% that was left behind, turned out to have a property of extraordinary consequence. When uranium-238 captures a neutron, a slow neutron, or even a fast one under the right conditions, it becomes uranium-239, which is unstable. It undergoes beta decay, emitting an electron and transforming one of its neutrons into a proton, and in doing so it becomes element 93, neptunium-239. And neptunium-239 is also unstable, also undergoes beta decay, with a half-life of approximately 2.4 days, and becomes element 94, plutonium-239. This is the transmutation. This is the act of creation that I spoke of. Not creation from nothing, but creation from something that was already there, something abundant, something that nature had provided in enormous quantities, and that we, by subjecting it to a flux of neutrons, transformed into something nature had not provided at all. The discovery was made in December of 1940 and confirmed in February of 1941 at the University of California at Berkeley by Glenn Seaborg, Edwin McMillan, Joseph Kennedy, and Arthur Wall. Seaborg was a young chemist, brilliant, methodical, possessed of the kind of patient experimental genius that I, as a theorist, could admire without fully sharing. He and his team produced plutonium in quantities measurable only in micrograms, millionths of a gram, using the 60-inch cyclotron that Ernest Lawrence had built. They identified it chemically, determined its nuclear properties, and, this is the critical point, they discovered that plutonium-239, like uranium-235, was fissile. It could sustain a chain reaction. And its fission cross-section for slow neutrons was even larger than that of uranium-235, approximately 742 barns compared to 585 for uranium-235. A barn, I should explain for those unfamiliar with the unit, is a measure of the effective target area that a nucleus presents to an incoming neutron, 10 to the negative 24 square centimeters. The name was a joke among physicists during the war. Compared to other nuclear cross-sections, these fission cross-sections were, as someone put it, as big as a barn. The humor of physicists is not always distinguished, but it is occasionally apt. The significance of this discovery cannot be overstated, and I say this as someone who was involved in assessing its significance at the time, before Los Alamos, before I had been asked to direct anything at all. The significance was this. Plutonium-239 could be produced from uranium-238 in a nuclear reactor. You did not need to separate isotopes, that agonizing, energy-devouring process of distinguishing atoms that differ by only 3 neutrons out of 238. You needed only to build a reactor, fuel it with natural uranium, surround it with a moderator to slow the neutrons, and wait. The uranium-238 would capture neutrons and transmute over a period of days into plutonium. And then you could separate the plutonium from the uranium chemically, a far simpler process than isotopic separation, because plutonium is a different element with different chemical properties, and chemistry has been separating different elements for centuries. This was the path that Enrico Fermi opened when he achieved the first self-sustaining chain reaction at the University of Chicago on December 2nd, 1942. That reactor, the Chicago Pile 1, or CP1 as it was designated, was not built primarily to generate power or to demonstrate a principle. It was built to prove that plutonium could be produced. And it could. Within months, the plans were drawn for the massive production reactors at Hanford, Washington. 3 reactors, each one larger and more powerful than anything that had existed before, cooled by the waters of the Columbia River, operated around the clock by thousands of workers who, for the most part, did not know what they were making or why. By 1945, the Hanford reactors had produced enough plutonium for the Trinity test and for the bomb that was dropped on Nagasaki. The total amount was not large. The critical mass of plutonium-239 is approximately 10 kilograms, a sphere roughly the size of a baseball. 10 kilograms, the weight of a small dog. And with that quantity, compressed by shaped explosive charges to roughly twice its normal density in a process called implosion, a process whose development consumed some of the most brilliant engineering minds at Los Alamos, minds like those of Seth Neddermeyer, who first proposed it, and George Kistiakowsky, the explosives expert who made it work. With that quantity, we achieved a yield of approximately 21 kilotons at Nagasaki. 21,000 tons of TNT equivalent from 10 kilograms of an element that had not existed on Earth in any detectable amount until 4 years earlier. I would not have you think that this was a simple or inevitable process. It was not. The physics of plutonium turned out to be devilishly complicated, more complicated than we had anticipated, and we had anticipated a great deal of complication. Plutonium has 6 allotropic forms, 6 distinct crystal structures, more than any other element in the periodic table. It is brittle in some phases, ductile in others. Its density varies from 16 grams per cubic centimeter in the alpha phase to less than 16 in the delta phase. It expands when it solidifies, like water, one of the very few metals to do so. Its metallurgy was a nightmare. The men and women who worked with it at Los Alamos, Cyril Stanley Smith, the metallurgist, Eric Jetty, and others, spent months learning how to cast it, machine it, shape it into the precise geometries that the implosion design required. And there was, of course, the additional complication that plutonium is extraordinarily toxic. An alpha emitter with a biological half-life in bone of approximately 200 years, meaning that once it enters the body, it remains there essentially forever, irradiating the surrounding tissue. The maximum permissible body burden was set during the war at 5 micrograms, 5 millionths of a gram. We handled it with care. We did not always handle it with sufficient care. The long-term health consequences for some of those who worked with it are a matter of record and of conscience. But there is another dimension to this story, a dimension that I think is perhaps the most troubling of all, and that I have turned over in my mind many times since the war. It is the question of what it means to create something that nature did not create, or more precisely, that nature created and then allowed to vanish. Because plutonium did exist once, in a sense. When the Earth formed, approximately 4.5 billion years ago, from the gravitational collapse of a cloud of gas and dust enriched by the debris of earlier stellar explosions, supernovae, which forge elements heavier than iron in the cataclysm of their dying, there would have been plutonium present in the primordial material. Plutonium-244, the longest-lived isotope, has a half-life of approximately 80 million years. This seems a long time by human standards. It is not long by geological standards. After 4.5 billion years, roughly 56 half-lives, the amount of primordial plutonium remaining on Earth is effectively zero. It has decayed, atom by atom, through alpha emission and spontaneous fission, back into lighter elements. Nature made it, and nature unmade it, over a span of time so vast that it dwarfs the entire history of life on this planet. And then we made it again, in 4 years. There is a passage in the Bhagavad Gita, chapter 11, verse 32, which is the passage that came to me at Trinity, though not in the form in which it is usually quoted. The usual translation is, "Now I am become death, the destroyer of worlds." But a more literal rendering of the Sanskrit, Kaloshmi lokakshayakrit pravriddho, is something closer to, "I am time, the mighty destroyer of worlds, here engaged in destroying." Time, not death. Time is what destroyed the primordial plutonium, atom by atom, over billions of years. And what we did, what Seaborg did in his laboratory, what Fermi did beneath the squash courts at Chicago, What the reactors at Hanford did on an industrial scale was to reverse the work of time, to bring back into existence a substance that time had patiently erased, and to do so not out of reverence for the deep processes of nature, not out of a desire to understand the nucleosynthesis of the stars, though both of those motivations were present, and I would not deny their sincerity, but because we needed it for a weapon. One might stop here and feel that the moral picture is adequately drawn. It is not. Because the creation of plutonium did not end with Nagasaki. The reactors continued to run. New reactors were built at Savannah River in South Carolina, at other sites around the world. The Soviet Union built its own plutonium production reactors, beginning at Chelyabinsk 40 in 1948, using information that was, in part, obtained through espionage. The case of Klaus Fuchs, who worked at Los Alamos and passed detailed information about the implosion design to Soviet agents, is well documented and need not be rehearsed here, except to note that the information he passed was specifically about the plutonium bomb, not the uranium bomb, because it was the plutonium bomb that represented the more sophisticated and more scalable design. Britain, France, China, Israel, India, Pakistan, North Korea, each in turn chose the plutonium path. And the total quantity of plutonium that now exists on Earth, produced by reactors, separated by chemical processing, fabricated into weapons or stored in vaults, is estimated at approximately 500 metric tons. 500 metric tons of an element that does not exist in nature. Enough, at 10 kilograms per weapon, for 50,000 nuclear warheads. And plutonium-239, once created, does not conveniently disappear. Its half-life is 24,110 years. It will be here, in the weapons, in the waste, in the soil around the production sites where it was manufactured with insufficient caution, in the sediments of rivers, and the bones of those who were exposed to it, for a period roughly 5 times the span of all recorded human history. We have introduced into the world a substance that will outlast our civilizations, our languages, our religions, our memory of why we made it in the first place. The pyramids at Giza are 5,000 years old and already crumbling. Plutonium-239, produced at Hanford in 1944, will still be radioactive when the pyramids are dust. I've been wrong about many things. I was wrong, I can say this now with the clarity that comes from having lived with the consequences. I was wrong to believe that the creation of the bomb would lead, swiftly and naturally, to the international control of nuclear weapons and the abolition of war. I believed this. Many of us believed it. Niels Bohr, the deeply creative, subtle, and critical spirit who guided, restrained, deepened, and finally transmuted the enterprise, Bohr believed it with particular fervor. He went to Churchill. He went to Roosevelt. He argued with all the eloquence and all the authority that a man of his stature could bring to bear that the bomb had made war between great powers impossible, and that this impossibility, if properly understood and properly managed, could become the foundation of a lasting peace. Churchill dismissed him. Roosevelt listened and did not act. And the arms race followed, as arms races always follow, when the logic of fear is stronger than the logic of cooperation. I was wrong about that. But I do not think I am wrong about this, that the creation of plutonium represents a threshold in the relationship between human beings and the natural world that is different in kind, not merely in degree, from anything that came before. We have always modified nature. We have bred crops and domesticated animals and dammed rivers and cleared forests and extracted metals from ores. But we have never before created a new element, a substance with no natural analog, no place in the existing ecology, no function except the one we assign to it, and released it into the world in quantities sufficient to contaminate the planet for geological spans of time. We have added something to the earth that was not here before, that was not meant to be here, if one may speak of nature as having intentions, which is a metaphysical question I do not pretend to resolve, and we cannot take it back. The half-life is the half-life. The physics does not negotiate. There are children playing in the streets who could solve some of my top problems in physics, because they have modes of sensory perception that I lost long ago. And I think sometimes that those children who know nothing of neutron capture or beta decay or cross-sections measured in barns, who have never heard of Seaborg or Fermi or the Hanford reactors, that those children, in their innocence, may understand something about the creation of plutonium that we who created it have found it convenient to forget. They understand, without being told, without needing equations, that there are some things you should not make, not because you lack the ability, but because the making of them changes you and changes the world in ways that cannot be undone. This is not a counsel of ignorance. I would not have you think that I am arguing against knowledge, against the deepest impulse of the scientific spirit, against the belief that it is good to find out how the world works. I still believe that. It is not possible to be a scientist unless you believe that it is good to learn. It is not possible to be a scientist, and it is not good to be one, unless you think that it is of the highest value to share your knowledge, to share it with anyone who is interested. I believe these things as deeply as I believe anything. But I have learned, and the learning has cost more than I can easily say, that knowledge and the application of knowledge are not the same thing. That understanding how to create plutonium and choosing to create it by the ton are separated by a chasm that no equation can bridge, and that the responsibility for crossing that chasm falls not on the physics, but on us, on men and women, on the choices we make and the choices we fail to make, and the consequences we must live with either way. Prometheus stole fire from the gods and gave it to mankind, and for this he was chained to a rock while an eagle devoured his liver, which grew back each night so that the torment could be renewed each day. It is a story about the cost of giving humanity a power that the gods had reserved for themselves. But there is an aspect of the Promethean myth that is seldom remarked upon, and it is this: the fire already existed. Prometheus did not create it. He merely transferred it from one realm to another, from the divine to the human. What we did with plutonium is something different. We did not steal this fire from the gods. We made it. We made it ourselves, in our own laboratories, with our own hands and our own mathematics. And if there is a punishment for this, and I am not sure that punishment is the right word, but I am not sure that it is the wrong one either. If there is a price to be paid, it is not that an eagle will come. It is that the thing we made will be with us, in our soil and our water and our bones and our politics and our nightmares, for 24,000 years. And we will have to find a way to live with it, or it will find a way to outlast us. Dante, in the 17th canto of the Inferno, describes the monster Geryon, the embodiment of fraud, who carries Dante and Virgil down into the lower circles of hell. Geryon has the face of a just man, the body of a serpent, and a tail that ends in a poisoned sting. And I have thought more than once that plutonium is something like Geryon, a thing with a just face, because the physics that produced it is honest physics, because the science is real and true and beautiful, in the way that all deep science is beautiful, because the chain reaction and the transmutation of elements are among the most remarkable achievements of the human mind. But the tail, the 24,000-year half-life, the alpha particles lodging in bone, the 50,000 potential warheads, the contaminated landscapes that will remain hazardous long after the civilizations that contaminated them have been forgotten. The tale carries a sting that we have only begun to feel. I said once that science is not everything, but science is very beautiful. I have not retracted that, and I do not retract it now. The physics of plutonium, the neutron capture, the beta decay, the nuclear shell model that explains why certain configurations of protons and neutrons are more stable than others, the liquid drop model that describes fission itself. All of this is beautiful. It is beautiful in the way that a piece of mathematics is beautiful, in the way that a fugue is beautiful, in the way that the Gita is beautiful. Beautiful because it reveals a coherence in the world that was not apparent before, because it shows us that the universe has a structure and that the structure can be known. And I would not give up that beauty. I could not, even if I wished to, because it is part of who I am and part of what it means to be a physicist, and to deny it would be a kind of lie. But beauty, I have learned, is not innocence. The most beautiful theory in the world can produce the most terrible consequences. The most elegant experiment can open a door that cannot be closed. And the element we created, this strange, dense, silvery metal that tarnishes to gray and then to blue and then to a dull olive when exposed to air, that is warm to the touch because of its own radioactive decay, that sits in vaults and in warheads and in waste repositories around the world, patient as time itself. This element is the permanent record of what we chose to do with what we understood. There are no secrets about the world of nature. There are secrets about the thoughts and intentions of men. The physics of plutonium is in the textbooks, available to anyone with the training to read them. But the question of why we made it, and whether we should have made it, and what we owe to the future that must live with it, these are not questions that physics can answer. These are questions for us, for men and women, for beings who are capable of creating an element that nature discarded billions of years ago, and who must now find the wisdom, if wisdom is possible, if we are capable of it, and I confess that I am not certain, the wisdom to bear the weight of what we have created without being crushed by it, and without pretending that it is lighter than it is. The peoples of this world must unite, or they will perish. I have said this before. I say it again, not because repetition makes it more true, but because the passage of time has made it more urgent. Plutonium does not decay on a human time scale. It does not forgive. It does not forget. And it will be here, in this world that we have altered in ways we are only beginning to comprehend, long after every one of us, and every one of our children, and every civilization we can imagine, has returned to the dust from which, like plutonium itself, though by very different processes, we were once assembled. We made this element. It is ours. And the question of what it means that we made it, what it says about us, about our brilliance and our folly, about the distance between what we can do and what we should do, that question, I am afraid, will last as long as the plutonium itself.